Let me begin with a word of prayer. Dearly Father, we thank you for your creation and all the many things that you've allowed us to understand, even if it's just a small part of what's really there. We just pray that you be glorified and lifted up in what we do, Lord. In your name I pray, Lord Jesus. Amen. So let's see here. So we have introduced the exterior derivative. We now have differential forms we can play with on a manifold, which is super fun. And the next thing you want to do in this world of discussion is talk about how to move the differential forms around. And so that brings us to what's called the pullback. And so I think mostly today we're just going to be talking about the pullback. That'll probably be all we do today, in all likelihood. So let's get into it. So let me just draw a picture of the pullback. So it's something like this. You've got a manifold M, you've got some kind of smooth mapping F, right? You got some other manifold over here, N, all right? And you're given a K-form on N. And so we're going to use the notation omega as an element of the K-forms on N. And I'm just talking about this as if the K-form is defined on all of N. But of course you could localize this concept to say a K-form defined on some subset of N, right? And on the converse side, if you want to be more deep about that, any differential form that you defined on an open subset of N, you could extend to be a differential form defined on the totality of N by sort of just extending it to be 0 away from where you've already defined it. And you can do this carefully if you've got something called a bump function, but that's a longer story that belongs in the course after this one. But then over here, we'll talk about the pullback of omega, which we use an upper star pullback of omega. And that, we're going to see, is a K-form on M. All right. So, unlike the exterior derivative, we don't change type, right? We're not going from a P form to a P plus 1 form or anything like that. It's just, in some sense, moving the differential form back from N to M. And so here's how it goes. The definition essentially is this: the pullback of omega. Now we have to do it at a point, all right, at the point P. It is, how do you define a K-form? Well, you got to define how it acts on a K-tuple of vector fields, yeah? Of vectors, rather. X1, X2, xk. So these guys are where? These would be all where in TPM, right? Those are all, each entry there is a tangent vector at P, all right? And so what's that going to be equal to? That's going to be equal to omega at F of P, all right, acting on dpf of x1, dpf of x2, and finally dpf of xk. Now, I will admit, Ernesto, I have not been super careful in these notes about whether I'm writing this or whether I'm writing that, okay? So I wouldn't make much of that distinction because I haven't made the distinction. So, of course, this is for k greater than 0, all right? This is how we define the pullback All right. Now, what about a zero form? What if we had a zero form? If, let's say, g, which would be what? G would be a function from n to r, right, is a zero form. So a zero form, remember, is just a function on n. Then the pullback under f of g, right, is actually a zero form on m. And that, of course, is the smooth functions on m. All right, zero forms are just smooth functions. And what do you think the definition of the pullback of a function would be? See, we used the remember, we used the differential here. Remember, the dpf is a mapping from tpm to tf of p n, right? That was the differential. So that makes sense. Like, if you just think about it, every one of these guys is where? These are in the tangent space at f of p to n. So it makes sense that we're evaluating that k form at f of p on that k tuple of vectors at f of p tangent to n. But here, what's this? It's a zero form. It doesn't eat vectors, right? It's just a function. So we have to say what? F star of g, right? So I guess feet at a point. What's it going to be equal to?
Equal to the differential of the function.
But it's not. It's a zero form. It's just a function. I need to just tell you, I need to give you a real number, somehow or another, and I need to use f and g. It's all I got. So how about this? F of p. So if I start with p, right? P's here in m. Then over here you've got f of p, which is in n, right? And if I feed f of p into g, that gives me a real number. So I should do g of f of p. That would be something I can do. And in other words, in short, the pullback of a function is just the composite. So far, so good? Yeah. Let's see here. Let's see if we can actually work this out for a silly example. Example 1. What if I had like f of x comma y equal to, let's say, I don't know, x plus y, x minus y. This may be too silly to really appreciate much from, but this will work, right? Here, I'm looking at f as a mapping from M to N, where M equals to N equals to R2. And we can look at, well, what's a differential form? And so let's actually do a little bit. Let's be a little bit more crafty here. Let's call XY coordinates for the domain, and let's use UV coordinates for the codomain. They're both R2, but I'm going to put UV coordinates on N, and I'm going to put XY coordinates on M. All right. So M, N. All right. So to take this thing for a spin, let's start out with zero forms. What would a we take a what? We're supposed to take a function. So we think about f g basically equals to a function of u and v, right? If you allow me that notation, this is, here g is an element of the zero forms on n, all right? What would the pullback look like? Pullback of g at the point x naught, y naught, what would that do?
G composed
Cool.
x naught, y naught.
Yeah, g composed with f of x naught, y naught, which would be g of x naught plus y naught, x naught minus y naught. Or if we write it in terms of xy notation, we've got f composed with g, f pullback g of xy is straight up equal to g of x plus y, comma x minus y. Let's put that into a sentence. What's going on here? What is the pullback? So we take u and v and substitute u equals to x plus y, v equals to x minus y. That's the pullback. It's a substitution in this context. Okay, so let's try this out on something a little bit more interesting. Let's look at a one form. Let's say alpha. Oh, I guess I should say omega to keep with my notation. Let's say omega equal to u squared dv plus v squared du. All right. And let's calculate the pullback of this guy. So f pullback omega. All right. So it would be equal to f pullback omega acting on partial x dx plus f pullback omega acting on partial y dy. Because any one form, right, any one form on the plane using xy coordinates can be expanded in as such, right? Now how does that actually go? So this is supposed to be what? This is supposed to be omega of df of partial x, right? Omega of df of partial y. And I hope you don't mind that I'm just omitting the point dependence. Which would have driven undergraduate me absolutely bonkers. But let's try to see the forest for the trees here for a minute. And I sometimes spend too much time looking at the trees. So what's that? what is df of partial x? Well, that is let's see here. Let me, if I can put that into, that would be like omega of, we got ourselves partial f1 with respect to x partial u plus partial f2 partial x partial v. So this is f1, this is f2. Those are the component functions of f in the UV coordinate system. And of course that's specifically, and like likewise over here, right? So we have partial f1 partial y partial u partial f2 partial y partial v. What is partial f1 partial x? It's 1, right? What is partial f2 partial x? It's 1, right? Partial f1 partial y is 1. Partial f2 partial y minus 1. So what we got here is omega of partial u plus partial v times dx plus omega acting on partial u minus partial v dy. But what is omega of partial u? What is omega of partial v actually equal to? You know, feed these, let them act on partial u, and it picks up a v squared. And the u1, excuse me, the v1 picks a u squared. So what we got here? We've got u squared dx. Oh, wait a minute, did I do that right? Oh, yowzers, I got to think more. I'm going to continue this calculation. Let me continue this calculation up. Up here. Wasn't the path you expected, but it's the path I took. Let's see here. So then we got ourselves f star omega. It is, let's see here. So we get, I guess u squared plus v squared, right? Or v squared plus u squared. V squared plus u squared dx plus what? V squared minus u squared, right? dy. But what are u and v? As they relate to x and y? I mean, technically, I'm supposed to, I should be getting a formula with just x's and y's in it at the end of the day, because I'm pulling back my, I'm pulling back the one form, I'm pulling back omega over here in our UV space over back to our XY space. So here's my pullback omega over here, right? So I really, I would like to write the answer completely in terms of XY at the end of the day. Although I guess, well, I don't know. Um, sorry, a moment of indecision. What is, if this is, I guess this is where this is the point at which ignoring the point dependence has caught up with me. So let's think about it here. The pullback at the point P, right? I'm supposed to look at this guy at F of P, right? So I'm thinking of F of P here as being equal to like the UV, you know? But, so I guess that means that this is U and that's V. So if I go back to, you know, using P as X comma Y, thinking of it as that, excuse me, what's this squared plus that squared? It's what, like 2x squared plus 2y squared, right? The cross terms cancel, right? And then v squared minus x squared, it would be, now the cross terms don't cancel, everything else cancels, right? So like this squared minus that squared, x squareds cancels, y squareds cancel, and you get minus 4xy, right? Cool? Good. I'm not sure I believe it, but it is what we found. All right. So I believe I have essentially used the definition, gone through the process, you know, abusing notation a bit, but not too much. Just a little. Let's try this calculation a really different way. So I had omega is u squared dv plus v squared du. And ultimately, I observed that we're really looking at u equals to x plus y, and v is equal to x minus y. Right? So, oh, you got it already?
Yeah.
Cool. So then du is dx plus dy, dv is dx minus dy, and then omega is x plus y squared times dx minus dy plus x minus y squared times dx plus dy. And that is x squared plus 2xy plus y squared times dx minus dy plus x squared minus 2xy plus y squared times dx plus dy. Let's collect our stuff together. We got ourselves a what? X squared plus 2xy plus y squared plus x squared minus 2xy plus y squared dx plus, in the y, we get minus, so we get a minus 4xy dy. What do you know? So we get 2x squared plus 2y squared dx minus 4xy dy. Wow, wait, how does that work? So one way to think about the pullback is it's just substitution. Now, let me be less informal and state these things carefully. The careful statement of the calculational hubris I just made is this. So this is properties of the pullback. What are the properties of the pullback? Well, the properties, they are as follows. The pullback of A omega plus B tau is A times the pullback of omega plus B times the pullback of tau. Now here, omega and tau are elements, they're k-forms on n. All right, and we'll let f be a mapping from m to n, you know, a smooth map, okay? I just have C1 in the notes, but whatever. Now here, A and B, just real numbers, okay? So that's number one. Number two, the pullback of the wedge product is the wedge of the pullbacks. Number two. Ooh, look at this one. Number three, check this out. The pullback of the exterior derivative of omega is the exterior derivative of the pullback. So before I get lost in proving these, all right, let me just try to explain why my calculational method makes sense. So if we have, supposing the properties are true, okay? If omega is equal to the sum over multi-index I of omega I dxi, right? So here, omega I would be, you know, a smooth function from n to the reals, right? For all choices of multi-index I. And dxi is again a notation for like dxi1, wedge dxi2, dxik if we're talking about a k-form. So if I take the pullback of omega, how's that go? So let me just get to the point here. Using the inductive extension of number one, I can rewrite this as, well, it's really just the sum over I, right? Of the pullback of omega I dxi. By the way, you could put a wedge here if you wanted, but we just don't typically write the wedge product between zero forms. You know, this is, I mean, I could put a wedge there. Maybe I will, just for the sake of emphasizing. We usually opt not to, but I'm going to opt to do it here. And the reason I'm going to opt to do it here is because then I will use property 2. And when I use property 2, see what I've got? I've got f pullback omega I wedged with f pullback dxi. All right. Now, what is the pullback of this function? It's just composition, you see? So that's literally, I just take omega I and I compose it with f. All right? And over here, notice that this is, by property 3, the pullback of dxi is the differential of the pullback of xi. Ah, man. Dang, I can't quite. That's a lie. That's a lie. It's a believable lie, but it's a lie. I gotta interact with this notation here, unless I want to invent whole new notational schemes to avoid that. But listen, so this is really f star of what? Of dx I1 wedged dx ik, right? But by repeatedly applying step, well, I guess first of all I can just repeatedly apply number 2 and get myself to this, right? Let me just get, I don't have enough board space. Right? So the pullback of the wedge product is the wedge product of the pullbacks. If it's true for 2, it's true for 3, it's true for 4, it's true for k. And then I apply property 3. And see, this is, you know, the differential of the pullback of xi1. Wedge differential of the pullback of xik. And, well, there you go. I mean, it's the differential of the pullback of xi1 wedge wedge differential of the pullback of xik. And I guess if you're willing to join me in this madcap adventure of slick notation, we could write this as omega I composed with f, the differential of the pullback of f with x multi-index I, with the understanding that this means that. Okay, introducing yet another notation. But what does this mean? The pullback, first of all, the pullback of f with xi is really what? I should have emphasized what that is. That is just composition of xi with f, right? Sorry, I buried the, that was actually the point. Which is really just a fancy way of saying the component, the I1th component function of f, the ikth component function of f. What is this actually saying? It's saying you take the formula for omega and you substitute the formulas for f. So like that's what I did here. I took the formula for omega, u squared dv plus v squared du, and I plugged in f1 and f2, which were x plus y and x minus y. Now, of course, if we actually go through the business of tracking the definition of the pullback faithfully according to like what's written down, it takes a long time, like my example 1, right? But once you understand what's going on here, you can calculate pullbacks quite quickly, because it's just a natural extension of the differential calculus, which we've already learned like a little bit in calculus 3. It's just the next level of substitution differential stuff. All right, let's try to prove. So my notes, it says the proof of 1 is clear. I think that's actually not one of those you know, ha ha ha, it's clear proofs. That's like, no, it's actually pretty clear why the pullback is linear, because the pullback is defined in terms of the K-form acting on differentials. And so the K-form is assumed to be, it's a tensor, so it's multilinear. But you'd have like, yeah, fine. Maybe it's clear, maybe it's not clear. Maybe it's actually worth maybe it's worth 5 minutes to actually explain why it's quote unquote clear. All right, so what would this will be a good warm up for the next one. Pullback A omega plus B tau. We'd have to let that act on what? At the point P, right? And it eats what? It eats the K tuple of vectors, right? But then by definition, that is A omega plus B tau at the point what? At the point F of P. And it gets fed dpf x1, dpf xk, right? But then this is literally A omega f of P times all that stuff plus B tau f of P times all that stuff. Why is that? Well, that's the definition. That's the definition of addition of functions. It's just function addition. I didn't even need, I don't think I even need the tensorial property of the K-forms here for that. Goodness. It really is clear. And then what is that? Well, that's the pullback of omega times A plus B times the pullback of tau, right? All acting on my K tuple. Skipping a few steps, but yeah. And this is at the point P, of course. And since that holds for arbitrary K tuples, number one follows. Is that reasonable? The next one, I think, is a little bit slipperier. Let me be careful. Ish. So part 2, we will look at the pullback omega wedge tau at the point P. That's funny. I got a square bracket just left over there. Whatever. x1 dot xk plus L. All right, so I'm assuming omega is a K form, I believe. Yeah, omega's a K form on N, and tau is an L form on N. All right. I don't know why I'm putting these parentheses in. We don't need, we got enough parentheses floating around already. I don't need to start introducing more parentheses. Brief. I have a bad habit of inventing parentheses where they don't need to be. All right, so definition, this is omega wedge tau at the point P acting on what? dx, dp x1 dot all the way out to what? dp xk plus L, right? That's the definition of the pullback. Is and I seem to be missing a very important letter here. Do you see what I'm missing? Don't see it? I'm missing what's that? What am I missing here? Anything stick out at you? I had it up here. Yeah, they're missing the F. Definitely need an F. Otherwise, it's not. Yeah, just fix that. So dpf of x1, dpf of x, k plus L. All right, great.
Do we want F of P after which?
No. Oh, omega f of p. Yes, we do that. Thank you. Very good point. That should be at f of p. Thank you. Excellent point. Then how do we compute that? How do we calculate that? So at this point, I drop some combinatorial. Take us back to, well, that was the sum over permutation sigma, sine of sigma, right? And then we do omega tensor tau at the point f of p, right? Acting on dpf of x sigma of 1, dpf dpf x sigma of k plus L. All right. Okay. But then we know how okay. But you remember how the tensor acts on a tuple? It just eats it, right? So like that is just, I'm going to move this over here just a bit. The sum over permutations sine sigma, and then we've got like omega of dpf, and omega, fine, omega f of p, dpf of x sigma 1, omega f of p. Oh, I'm a dummy. What does omega take? It doesn't take in one entry. It is a k form. It takes in a k tuple. So this goes on, right? Until you get to the kth one, dpf of x sigma of k. All right. And then we pick up on our tau of f of p, acting on dpf of x sigma kl, k plus 1 rather. And that goes on until finally you get dpf of x of sigma k plus L. So we good? All right. Then notice that we can rewrite that as the pullback. So the next step is to claim that this is what we're looking at here is, yeah, that's exactly the pullback of omega at the point P acting on x of sigma 1, x of sigma k, I think. And likewise, the other guy over there, pull back on tau at p, acting on the next bunch of them. Tau pullback, f pullback tau rather, at p, x sigma k plus 1, x sigma k plus L,
Are we supposed to have a product?
well, yeah, this is literally just a product of numbers here, but it's completely anti-symmetrized. It's the completely anti-symmetrized. It's a completely anti-symmetrized product of all these things, which means that that is equal to f star, pullback of omega at p, wedge the pullback of tau at p, all of that acting on the tuple x1 x k plus L. So in order to take the wedge product of two k-forms, you define it to be the completely anti-symmetrized sum of, it's basically, this is the definition of the wedge product of them, is what's going on here. And then since that holds for an arbitrary k-tuple, we've got this one right here. So that leaves us to number 3 to prove, right? Let's see if we can prove 3. I guess I got to erase my example 1 to prove 3 probably. Pretty happy about example 1. I think that was just the right level of not being too trivial and yet showing you how things work, you know? Pretty happy about that example. Let's see here. So we're trying to prove property 3. So what we'll do is we'll start out with the pullback of the exterior derivative of omega. All right, and that's going to all be going on at the point P, and since omega was a k-form, we're going to have to look at a k plus 1 tuple of vectors, right? Because the differential of a k-form is a k plus 1 form. So we got this. All right. So by definition, what we got here? We got d f at the point f of p, right? Acting on the differential at p of f of x1, right? And so forth and so on all down the line until we get to the differential at f of x k plus 1. Let's see here. So what do I do next? Oh, Now, beware, the calculation on page 243 uses the repeated index notation. Let me undo that here. So we're looking at the sum over I, all right, of omega sub I oh, my bad. It's sum over I, sum j, right? And you've got like, oh, good grief. Partial omega, oh, this feels wrong. Partial omega I, partial x j, dx j wedge dxi. That's my differential, that. I'm sorry, that feels wrong. That feels wrong. But that's what I did. So, all right. Acting on this, right? So how does that actually go? Well, let's see, did I use these? Okay, no. So, all right. See if I can come to terms with what the notes are telling me here. All right. So technically, this is at f of p, right? Because it's omega at f of p. And basically the point is, the way that this calculation goes is we can just pull the functions out, right? We can pull these functions out. All right. And then we're really just looking at dx j wedge dx, I1 wedge wedge dx I k, that thing, right? Acting on these guys. Okay, do you understand I'm basically just extracting the multiplication. I mean, this just multiplies this business here. Well, the sum, of course, I'm using a property of the sum, but for each term in the sum, we're going to have like this acting on that, but we can just pull that out because this doesn't actually engage in the operation of these guys on that. So I can just pull this out like that. And then I'm just have to think about how that works, right? And of course, we could let's see here. I feel like there may be some combinatorial hand waving in the notes at the moment. I mean, if I needed to oh, Okay. It's a reasonable thing, what's written in the notes, because what would this mean, if you can imagine in your mind's eye? This means to completely anti-symmetrize this. It's the anti-symmetrized tensor product of all these things, right? So we anti-symmetrize over the tensor product, right? Anti-symmetrize over the tensor product of that, right? So then what are you getting? You're getting things of the form, you either got your like dxj of dpf of x1, right? And of course it's not x1. After you do the anti-symmetrization, you're up against dx whatever, alpha, all right? And likewise, you know, the other ones are like what, dxi1, dxi sub j of dpf of x alpha, right? I mean, whatever. That's what happens once you anti-symmetrize the tensor product and you feed it this k plus 1 tuple, right? And that when you do that, you've got a product of things like that. But remember, this is what? That's really the differential. That is f, pull back the differential of xj acting on x alpha, right? And this is the pullback of dxij acting on x alpha, right? But then, since that's all happening in the completely anti-symmetrized tensor product, it's the wedge of these things. So that's why in the notes I just basically go from here to the next step, sum over I, sum over j, partial omega I, partial xj at the point f of p, and then we're looking at the differential of f pullback, f pullback the differential, my bad, I'll get it eventually, f pullback the differential of xj, wedge with f pullback the differential of xi1, wedge, wedge, f pullback the differential of xi sub k, all right? And that all acts on what? Well, x1, x2, xk plus 1. But notice that this is actually the pullback of partial omega I, partial xj, because it's composition. It's evaluation at that point. So I think at this point, we then, and of course, there's the optional wedge, right? Zero form, wedged with the k form, k plus 1 form rather. So then I think I fall back on properties 1 and 2 to pull the wedge, to look at this instead as the pullback of what? This is really the pullback